All right, so good afternoon. I think I introduced myself to, I think all of you. If I have not. Um, right, so I am assistant professor at UT Austin. I moved there in 2019, and before that, in fact, I was working first as a postdoc at JPL under Marco's supervision, and then UCLA. I loved LA a lot, but then, um, I got the job in Austin, and that's how I moved. Actually, I don't know what else I should say. Well, when I was your age, more or less, I was doing my PhD in Europe, and I was actually working on a magnetosphere. So I was working on simulations and observations of whistlers during reconnection in the magnetotail. So I thought I was set on my, magnetospheric path, but then, you never know what can happen. I switched to study waves and turbulence in the solar wind. And since then, I think I more or less stuck with that, okay? I guess the bottom line here is that, there are so many, opportunities and topics to be explored. Plasmas are plasmas. So I have here a few references for you in case you want to know more. These are pretty classic textbooks. And the last one is a review by Bruno and Carbone about turbulence in the solar wind. Okay, so this is the outline of this afternoon's lecture. It's kind of dense. Chances are I won't get to the end. So since I probably won't get to the end anyway, please do interrupt me if you have any kind of question. I will rather, slow down or spend more time to explain some concepts rather than, losing any of you halfway, okay? So I will start by giving you a general introduction of why we care about turbulence, although this morning we also had some compelling arguments. And then I will, point to some, specific reasons as to why we care about turbulence in the solar wind. Then I will introduce some basic concepts by using standard fluids as an example. In fact, the first, studies of turbulence start with, with fluids before moving to MHD turbulence. Okay, and then discuss how, how much of all of this work to explain observations. It's going to be maybe a lot of information, I guess. What I want you to learn really from this lecture is why turbulence is important, what are the main properties of turbulent flows, and beware that turbulence in magnetized plasmas is different, has some fundamental differences with respect to turbulence in standard fluids. Okay, ready? Let's go. So turbulence is a state of fluids. It's a phenomenon that we experience in our everyday life. And it affects, so every time we set fluids into motion, unless they are very viscous, like honey or Nutella, as we were saying the other day, well, unless you have those very viscous fluids, turbulence sets in anytime you set some motion, okay? And turbulence, in fact, plays a crucial role in many aspects of our life. I have here some examples, okay? So turbulence is a major factor in the current aviation industry, for example. That's because when you have an object moving through air, you create a turbulent boundary around the object, which increases drag. And so engineers study the best shapes that allow the flow to streamline as smooth as possible around the object to reduce this drag. Turbulence also is associated with chaotic motions that enhance mixing. So that's why you want to stir your coffee if you like it with milk, so that you mix them you can mix them well, okay? And so for this reason, turbulence affects transport of mass, momentum, heat, okay? So for example, turbulence is important to track, the spread of pollutant in the air. For similar reasons, turbulence also affects weather patterns. And for example, it can help to create conditions for the formation of hurricanes, okay? Now, in space, we care about turbulence because it can heat and accelerate the plasma, right? It can scatter cosmic rays, for example. And, besides our, our close, space environment, in interstellar space, turbulence is a major factor for star formation. So I found this cool video on YouTube, which shows, where's my phone? Okay, which shows turbulence in the air. The way it is visualized is by shining a green laser light through a glass rod on smoky air. So the glass rod diffracts the laser light, and the smoke diffuses the light so that you can actually see, okay? And believe it or not, there is not really a, come on, play. There is not really a definition of turbulence. But there are some canonical features that we can recognize in turbulent flows. They're generally unsteady, and they appear to be chaotic and intermittent, which means that you have, some, instances in which the fluid is very active, and some instances in which the fluid is more quiet. They are associated, like I said, with enhanced mixing, and importantly, they are multi-scale. So you can see in this image that you have structures, vortices on multiple scales at any given time. This movie here, which is developing slowly, shows the development of turbulence in a magnetized plasma, okay? So you can see that as time goes by, you are forming structures. So what you are seeing here in color code is the current density out of the plane, okay? In the XY plane, okay? And you have a strong magnetic field coming out. And so you can see that you are forming here structures that are qualitatively similar to what I showed you in the previous movie. So plasmas, especially collisionless plasmas, are not, strictly speaking, fluids, okay? But they do display similar properties. They display a collective behavior which manifests itself, for example, in the form of propagation of waves, and turbulence is another example. So in this lecture, I'm going to use the fluid description for plasmas, and in particular, the magneto-hydrodynamic description that, as we discussed, works fantastically well. So now let me tell you why we care about turbulence specifically in the solar wind. You have seen yesterday the Parker solar wind model. So this is just a quick, like refresh. So Parker put forward the first theory of a solar wind, starting from the steady state equations of conservation of mass here, and the momentum equation is the second equation in this slide. Rho is the mass density, U is the flow velocity, P is the pressure, C is not the speed of light, here is the sound speed, G, the gravitational attraction of the sun, R, the radial distance from the sun. So you can solve these equations, okay? And he argued that the only possible physically acceptable solution, although I'm sure that now you have been, better than I do. Okay, why? The acceptable solution is the one corresponding to the transonic solution, so a wind that becomes supersonic. So this plot here shows the flow velocity as a function of radial distance, where r is normalized to the solar radius. And you have a family of curves, each corresponding to a different temperature imposed at the base of the corona. So in this problem, the corona is assumed to be hot, but it isn't explained, okay, why in the first place. And I call this laminar because this flow that's predicted by this theory is smooth. And the flow follows well-defined streamlines, which are radial, right? As we saw yesterday. Just 1 year after that this paper came out, 1 year or so, okay, the solar wind was actually measured in situ. So although there was still, like a, I would say, like I say fight, not really fight, but a controversy on whether the solar wind existed or not. 1 year after the solar wind was measured, okay, which confirmed the existence of the solar wind, like Parker has said. So good. Now this theory is beautiful in its simplicity. However, it fails to explain a few important things. Okay, so let's take a look at how the solar wind looks like. Have you already seen this plot before? Yes, all of you in this school, probably. Okay, so I'm gonna go quick. So this is a composite image, okay, and it's a polar plot. Okay, it's a polar plot of the velocity measured as a function of latitude. And this is many years of observations by the Ulysses mission, okay, which is so far the only one who really explored the polar regions, okay? And this is superposed to a snapshot of a composition of white light images and ultraviolet images, okay? And this superposition is meant to guide the eye in finding correlations between wind structures and magnetic structures. So we can see here that there is a relatively steady wind coming from the highest latitudes, and then there is a highly variable, slower wind at the lowest latitudes in correspondence of closed magnetic field lines. So this is, first of all, to point to the fact that the magnetic field structure plays an important role to determine what kind of wind you get. The second thing I want to point out is that the relatively steady state wind predicted by Parker looks like the one coming from the highest latitudes. The color here of this, the blue and the red, represent the dominant polarity of the magnetic field. Okay, so what that means is that the wind here is coming out from, let's say, open magnetic field regions. Now, monopoles do not exist. Okay, so these field lines will connect out in interplanetary space. Okay, so the problem is that this wind is much faster than what the theory predicts. Okay, it's about up to 800 kilometers per second. With the Parker wind and reasonable temperatures at the coronal base, you can get beyond 400 or so kilometers per second. So there is an important mismatch between observations and predictions from the theory. The other problem is that if we adopt the standard laminar model of the wind, well, these kind of models underestimate the temperature of the solar wind that we measure in situ. So this is a plot of the temperature as a function of radial distance taken by the Helios mission, okay? And the solid line represents the best fit to a power law, which is reported here for reference. Now, the specific number in this case is not particularly important. What's important is that if the wind was expanding adiabatically, and adiabatic expansion is represented in this equation here, well, then the temperature will fall off much faster than observed. So this, in short, provides evidence that there has to be ongoing heating in the solar wind as it expands in interplanetary space. So there are two problems, okay? The solar wind is hotter and faster than theory predicts. And one of the scenarios is that waves can actually contribute to both heating and acceleration, okay? So this class of models, in fact, fall under the category of wave-driven winds. And these equations here are the starting point to describe these wave-driven winds, okay? So this is a upgraded version of the equations I showed you earlier, okay? These are still steady state, okay? However, well, the magnetic forces have been included, and and the effect of fluctuations has been included as well. So these equations have been obtained by assuming that there is a mean, an average wind, okay, plus fluctuations that are represented with these delta quantities. And these equations are obtained by taking the average. So this represents the average wind, okay? So if fluctuations have amplitude that are not negligible, okay? So if they are not small amplitude waves, then they do contribute to the average wind, and they can accelerate, okay? And the last equation here is a simplified form of an equation for the temperature, okay? That combines the adiabatic cooling as before, and it includes a source here, a heating source that comes from, in this case, dissipation of waves, okay? In fact, in this kind of models, this epsilon, which has the dimensions of energy per unit time per unit mass, well, it's like a fudge parameter where you kind of put everything that's not described by fluid models. Okay. Now, what lends support to these scenarios is that we do observe plenty of fluctuations in the solar wind. So by pure, I would say, casuality, okay, I'm showing here a plot of typical fluctuations we observe in the solar wind. So there are three lines here that correspond to fluctuations in the three components of the magnetic and the velocity field. And for each component, there are two lines, one representing the magnetic field, renormalized, and the other line for the velocity field. Now, take a look at this plot. Is there anything that ring a bell? Yes, who's speaking? Yes, and therefore, is that, yeah. So it's the Alfvén waves. Now, we have talked a lot about Alfvén waves yesterday, okay? So Alfvén waves are permeating the solar wind, okay? Now, the fact that we observe fluctuations that are, that look like waves, that look like Alfvén waves, so they are coherent in that sense, we shall see that poses a challenge at a fundamental level to the concept of the turbulent cascade. All right, so this is a recap, okay? What is one of the big problems? And understanding what heats and accelerates the solar wind. evidence suggests that fluctuations / turbulence might play a role in accelerating and heating the solar wind. Okay, well, then if we have identified a possible solution, what is the problem? Well, the problem is that we have to understand how the energy stored in the fluctuating fields can be ultimately released to the plasma. Okay, so to answer this question, we need to go beyond the laminar description of flows and beyond the description of linear waves that do not interact among each other. Okay, so this brings us to the topic of turbulence. And like I said, I'm going to start by introducing this topic by discussing turbulence in standard fluids. Questions so far? All good? You're with me? Sharp? Awake? Yes? Good. Okay. So early experiments on turbulence were performed by Reynolds in 1883. 1883. And Reynolds studied the behavior of flows in a pipe, okay? And he studied this behavior by tracking the evolution of a ink that will be injected into the flow itself. And Reynolds observed that the behavior of this flow will change dramatically, qualitatively, depending on a dimensionless number that later was called the Reynolds number. So the Reynolds number is defined as the typical mean flow velocity, U, okay, times the macroscopic scale of the system, L in this case is the diameter of the pipe, divided by the kinematic viscosity. So what he found is that for low Reynolds numbers, lower than something like 2000, the flow was laminar, okay? So what that means is that, the ink that he was injecting would follow a well-defined straight streamline, and there will not be mixing. As you crank up the Reynolds number, I might have said Lundquist number earlier. No, okay. The Reynolds number goes up above this threshold 4,000, and I don't think there is really an explanation as to why there is this critical number of the Reynolds number around 4,000. Then the ink would lose completely its coherence. It will start to form like eddies and spread across the cross-section of the pipe very rapidly. And that represents the turbulent regime. In between, you have an intermediate regime with intermediate values of the Reynolds number, where the ink will start to form like wavy patterns. However, there still will not be mixing really. And, although in this wavy pattern, the ink would maintain its coherence. And what I found here is on YouTube, a reproduction of these experiments. So the top movie that I'm gonna play corresponds to the laminar flow, okay? So this ink remains relatively on a straight line. The reason why you see this, kind of wavy things is because the ink is not being injected uniformly. And in fact, doing this kind of experiments accurately is very challenging. All right. The movie below instead corresponds to the turbulent case, high Reynolds number, which has been achieved by increasing the flow velocity. Okay. Now at this point, you can stick a hot wire into your flow and measure the velocity. And what I'm showing here is two experiments. So the measured velocity as a function of time in two experiments performed under the same conditions. What you notice is that, well, if you compare point by point the signal, what do you find? And the experiment is the same. Huh? It's noisy, yeah, that's right. What else? It's different. It's point by point different, right? So let me stop for a second here. So this is in apparent contradiction with the fact that this system is governed by deterministic equations, okay? And so there was this kind of, problem. So how do you explain that? Because for given initial, so this system is described by the Navier-Stokes equation for given initial condition, given boundary conditions, the system is deterministic, okay? So the answer to this apparent paradox was given much later in 1963 by Lorentz, okay, who demonstrated that there are some dynamical systems that are highly sensitive to small perturbations. So if you have, even tiny perturbations on the initial condition, you can get significantly different solutions, okay? However, even though these two signals are point by point different, they display the same statistical properties. Yes? The what? The ending? Ah, so you're still saying they're cheating here. It's possible. Well, I will have to resource this, and I'm not sure that this is the continuation of the other one. Well, that's the point. Okay, wherever you stick. Okay, so if you have a given flow, okay, you start to analyze it, okay, and you stick your probe in different positions, okay, you will get statistically the same results. And you can do the same experiment and stick wherever your probe, and you will get the same statistical results. So it's not surprising that there are indeed some similarities. I wouldn't venture to say that they are exactly the same split in two, but I might source this better. Okay, I guess check it out. So same statistical properties, the mean value, RMS. What else do you notice? Some already said, what do you say, like very noisy. So there are multiple scales. So this is the multi-scale nature I was saying before. By eye inspection, you can see that there are low frequency fluctuations, okay? And superposed to it, there are high frequency fluctuations, short scale fluctuations, okay? So even if you started from a smooth larger scale flow, soon after you end up having energy distributed over multiple scales. So the process of transferring energy from the larger scales to the small scales is also something that we experience in our everyday life. So let me go back to the example of the coffee with the milk. You know that you have to generate motions at very small scales, microscopic scales, in order to mix, your parcels of milk with parcels of coffee, and you start to stir with the spoon. Okay. However, the perturbation introduced by your spoon has a scale that's far from being microscopic, right? So there has to be some mechanism that kicks in and allows you to transfer this energy that you are injecting at the scale of the spoon, okay, all the way down to microscopic scales, okay? And at the basis of this phenomenon is the nonlinear transfer of energy through the formation, interaction, and destruction of vortices, okay? Now, there is no current framework that really captures how this process works actually, but the commonly accepted scenario is that there is an instability of these vortices, okay, that breaks them scale by scale. So this slide represents this process pictorially. So you start with, your large scale eddies or vortices at scale capital L. They become unstable and they break apart, generating smaller scale vortices of size L prime, a fraction alpha of the previous L, okay? And then the same process takes place so that the L prime vortices break apart, okay, giving rise to L prime prime vortices, a fraction alpha of L prime, okay? And so on and so forth. So this process proceeds self-similarly, okay? Until you generate small enough scales so that dissipation becomes faster than this instability process of the vortices, and that's where you end your cascade. So if you translate this from configuration space to Fourier space, this is what it looks like. So you have your injection scale here. And as you break apart your vortices and you're cascading the energy towards smaller and smaller scales, you are transferring energy in Fourier space towards larger and larger wave numbers until you reach the dissipation scale. And that's your source, okay? That's your sink of energy. Oops. Now, as we shall see, this is really described by Navier-Stokes, okay? However, to understand how this nonlinearity leads to the formation of smaller scale, it is very useful to use a simplified model, okay, represented by the one-dimensional Burger's equation, which contains the main ingredients that we are interested in. Okay, we have a nonlinear term, the nonlinear advection here, u d dx u, and then there is dissipation on the other side. Okay. Now let's assume that we have a periodic function for simplicity, and we can decompose it in Fourier series. So if you take this decomposition and you plug it into equation 1, you get equation 2, which is an evolution equation for the Fourier mode, for the amplitude of the Fourier mode k. Okay, so the dot here represents the time derivative. Okay. Now the trick is that the nonlinear term, when you move to Fourier space, introduces a convolution. Okay, and so this term, as you can see, involves different wave numbers, whereas dissipation acts on a given wave number. So if we take a look a little bit more in depth to what dissipation does, so let's neglect the nonlinear term, okay? What we obtain is a simple evolution equation for these amplitudes that you can solve, okay? And the solution is given by an exponentially decaying amplitude. So again, here it's clear that the dissipation acts on a single wave number, okay? You start with a given wave number and you end with that same wave number, okay? And the time over which it decays, okay, depends on viscosity, okay? And it depends on the scale. And it's faster the higher the wave number. It goes as k squared. So the smaller the smaller your scale, the faster it dissipates. Now, if we introduce nonlinearity, that changes completely the process, okay? The nonlinear term acts as a source, if you like, okay? Okay, let me rephrase this. The nonlinearity couples different wave numbers, okay? So even if you started with a single wave number, let's say wave number one wavelength in your box, okay? This term here at subsequent time steps acts as a source for exciting higher wave number modes, okay? And so this term, that's how you start to transfer energy across the scales, okay? Now, does this continue ad infinitum? So does this nonlinear term awakes all the modes accessible to the system? Well, the answer is already here, but what would you say? Yes or no? No, I mean, spoiler. Why? Why? I cannot hear. Well, yeah, I mean, dissipation becomes more and more important as K increases, okay? And at some point, this will start to dissipate faster than you know, than the process, the nonlinear process of transferring energy. So we can visualize this process by plotting the solutions to Berger's equation, okay? So what I show here is the solution to Berger's equation, okay, starting from the same initial condition represented by a sinusoidal function of one wave number into a box, okay? That's the solid line. The top row corresponds to a higher viscosity, and the bottom row corresponds to a lower viscosity. And for the Berger's equation, you can also, you can write it in dimensionless form and define a Reynolds number, okay? That in this case is defined through the length of the box, okay? So low Reynolds number on the top, high Reynolds number on the bottom. So initial condition, solid line, and then the subsequent lines, the dashed and the dotted line are two subsequent times, okay? And on the right column, I'm showing the corresponding Fourier modes, okay, as a function of time. No, as a function of K at different times. So initially, you only have one wave number, okay, in both cases. And then as time goes by, you see that you are forming a distribution. Okay, you're waking up higher wave numbers, okay? And if you compare the top with the bottom, what do you notice? Right, okay, which is the high Reynolds number case. Yeah. So in retrospective, if we think about the Reynolds experiment, what this is illustrating is that when the Reynolds number is low, then viscous forces dominate over inertial forces, and so they inhibit this formation of smaller and smaller scales. On the contrary, the high Reynolds number high Reynolds number case, the inertia term dominates, and it activates this, this cascade of energy. Questions? No.
Is it right that scale, the wave number K, always couples to scale 2K?
2K?
Is it always that, or can that vary sort of what scale couples to the next highest?
Yeah, no, this does not.
Like a few slides back, you would put it in terms of length scale L, you had this alpha, like L becomes alpha L prime.
Yep. Yep.
Is alpha always?
Oh, yeah, no. This is just for the purpose of just representation. No, it doesn't have to. Yeah. So I mean, really, the coupling of scales really depends on the underlying system, okay, and is represented by this term, okay. Now, one of the I'll come back to this, okay. So in general, so you have a non-local interaction, really, okay, of scales. One of the assumptions of turbulence is that really what's interacting is eddies that have nearly the same scale, okay? That's kind of the underlying idea of the turbulence phenomenology. All right. All right. Now, like I said, the theory of turbulence was really developed starting from the incompressible Navier-Stokes equation, okay, reported here. And even if, of course, they are more complex, the action of nonlinear inertial forces here and dissipation is really analogous. Okay, so you have the competition of two effects. Okay, dissipation on the one hand here, and the nonlinearities which tends to transfer energy across the scales. The important thing is that this energy transfer, in fact, happens conservatively. Okay, and this can be noticed or understood by looking at the energy conservation that you can get from the Navier-Stokes equation. So let us define a kinetic energy per unit mass, okay, which is the volume integral of 1/2 u dot du. Okay. So in order to get a conservation law for this quantity, you dot product with u your Navier-Stokes equation. Okay. Oops. Here. And so what you end up is that dk dt has three contributions. Okay. On the right-hand side is the contribution from dissipation. Okay. And then we have contribution 1 and 2. 1 comes from the pressure forces, and 2 is for the nonlinear advection term. And now you just, from your toolbox of, algebra, vector operator and theorems, okay, you can manipulate 1 and 2, okay, and you transform this in terms of volume integral of divergences, okay, and then you assume periodicity, okay, so that there is really no net effect from the fluxes at the surface, at the bounded surface. So contribution 1 and 2 integrate to 0, okay. The third term, which involves the viscous dissipation, is non-zero, okay? Can be rewritten in terms of the volume integral, okay, of nu, the kinematic viscosity, times the vorticity magnitude square. So what this tells us, okay, that this conservation law implies that the convective and the pressure terms do not alter the overall energy balance, but only affect its transfer across the scales, okay? And the only thing that affects energy balance is viscous dissipation. Now, you can have a forcing. You can force your system, just like when you're stirring your coffee, okay? You are injecting energy into the system. Or in the case of the sun is continuously injecting waves within the solar wind, okay? So if you add a forcing term here to the energy balance, this is what you get. And so the wonderful thing here is that you can achieve a steady state where dissipation balances injection. So the implications of all of this are two. Number one, I already said that the nonlinearities are responsible for transferring energy across the scales conservatively. And the other implication is that if a steady state is reached, what that means is that the mean dissipation rate per unit mass does not depend on viscosity. And this is the fundamental property of turbulence. Okay. Now, so far, okay, we have kind of presented a scenario with some quantitative elements of what happens in a turbulent flows, which is quite faithful, okay? However, without further hypotheses, it is not possible to develop a theory of turbulence from the Navier-Stokes equation, okay? And there are many questions that remain unanswered. For example, what happens between the scales where energy is injected and the dissipation scales? And when we say that small scales need to be reached, okay, how small are these small scales, okay? And so the answer to these questions were given by Kolmogorov, okay, in his theory of turbulence that I'm going to present here phenomenologically. Essentially, it is a phenomenological theory. And Kolmogorov developed this phenomenology of turbulence starting from three hypotheses that are motivated by empirical facts, okay? That at very large but finite Reynolds number, the turbulent flow is statistically homogeneous and isotropic. So wherever, so this is also why two signals may appear actually, the same. So homogeneous and isotropic means there is no preferential direction. And homogeneous, it doesn't really matter where you are performing your analysis, okay? Second hypothesis is that at very large but finite Reynolds number, the turbulent flow is self-similar at scales smaller than the injection scales and larger than the dissipative scale. Okay, so the self-similar thing that we saw with the hierarchy of eddies. The third hypothesis is that at very large but finite Reynolds number, the turbulent flow has a finite, non-vanishing mean dissipation rate per unit mass. Okay, and so the main elements of this phenomenology are the following. Okay, we have lambda, the scale under consideration. Okay, we have u lambda, okay, which is the typical value of the velocity associated to that scale, u lambda, okay, and tau and L, the nonlinear time or eddy turnover time associated with scale lambda. And if you take a look at your Navier-Stokes equation, you can see that this tau and L is I'm going to refer to this also as the nonlinear advection time, okay? So it's lambda over UL. It comes from, is U dot grad, essentially, the inverse of that. Okay. And so these are the three elements, okay? And then the hypothesis that he does is that eddies of nearly the same size interact through their gradients and distort and get destroyed. The intuition behind this hypothesis is that if you have a gigantic eddy and a smaller eddy, the gigantic one is going to advect the much smaller one, and the much smaller one won't really affect much the larger one, okay? So the most efficient interactions are between nearly same size eddies, okay? So under this hypothesis, okay, we can define the rate of energy transfer from scale lambda to the smaller ones, which is, well, the kinetic energy per unit mass that goes as u lambda squared at that scale, okay, divided by the nonlinear time, so the time it takes for your eddy at scale lambda to fall apart, okay? And that's our rate of energy transfer. Now, because, as we said, in the inertial range, I don't think I defined the inertial range. Do you want to know what that is? Yeah, we are, okay, so we are looking at the energy transfer rate. Okay, so we have u squared. Okay, that's proportional, so energy per unit mass, so there is a 1/2 that's missing, okay, but we have a nearly, so this wiggle, it's with the wiggle we indicate is nearly equal to up to a factor of order 1, okay? Divided by a time, so we want a rate. No, it's an energy rate. It's an energy per unit time. Right? So the inertial range terminology just made its way. So let me go back for a moment to clarify the terminology. So are there questions regarding this plot? All right. So the energy, the inertial range, okay, is the range of scales between the injection and the dissipation. So it's where you have this self-similar cascade, okay? And so this is where, the nonlinear essential inertial term determines the dynamics. Question? Oh, good. Half an hour? Plenty. Where were we? Okay, so we are interested in what happens in this inertial range, okay? And we wanted, and so, if the state of turbulence is statistically steady, then the rate of energy transfer from one scale to the next must be scale independent. So this pi lambda, the rate of energy transfer that we defined in the previous slide, and I'm just rewriting it here, must be constant, must be scale independent. And we call this epsilon, okay? And now we can obtain how the amplitude of the velocity fluctuations at scale lambda scale with the scale lambda, okay? So this is really a result. This could not have been predicted without the hypothesis that we made, okay? And what it tells us is that the smaller the scale, so the smaller your eddy, the smaller the associated velocity, okay? Yes. Yeah, so do you remember this? Yes. So this is swirling structures. And, these swirling structures are deformed. They have multiple sizes. So lambda refers to a given of this at a given length, lambda. Okay. Yes. Yes. This? Yeah. Yes. I'm sorry. I didn't understand the question. Yeah. Yeah, direct in this. Yes, correct. Yeah, direct in this. So maybe I should rephrase this in the sense that the transit of energy is across the nearby scales, and there is no. So this scale here per se is not gonna dissipate directly, but scales need to be smaller and smaller and smaller until they can be dissipated. But I mean, yeah, perhaps it's not the best way to describe this. Direct in the sense local at that scale, local in Fourier space. Okay. So if you look at this process in Fourier space, energy injection is far away and dissipation is far away. But it's indirect in the sense that energy is injected at a given scale and then it cascades. Of course, there is the effect of injection and dissipation through the turbulent cascade. It's semantic. Okay. Now, if we apply this concept of scale invariance of this energy transfer rate at the top of our turbulent cascade, okay, what we get is an expression for epsilon in terms of the macroscopic quantities. So epsilon is the energy injection rate, okay? And if we apply this at the bottom of our turbulent cascade, so we balance dissipation with epsilon, okay? Then we find finally the scale eta, and I apologize terribly of the abuse of notation. Eta here is not the magnetic diffusivity, okay? It's a scale that happens for historical reasons to be called eta. And so when we balance dissipation with our injection rate, then we find the scale at which the viscosity becomes dominant over the nonlinear term, okay? This is called the Kolmogorov scale, and it is proportional to the macroscopic length L times the Reynolds number to the -3/4. So the higher your Reynolds number, the longer is gonna be your inertial range, in such a way that you can achieve balance between injection and dissipation. Now, okay, maybe some of you have heard about the Kolmogorov turbulent spectrum. What's the scaling? What? Huh? Who says 5/3? Yeah, yes. Who says 5/3? Well, I guess it's here, okay? But you don't recognize it yet. So to make this result more familiar, okay, we can derive the prediction from this theory of the energy spectrum, okay? So we define an energy density in Fourier space, and you basically associate lambda to the inverse of the Fourier mode, okay? So if you do this operation, then from the scaling of U, okay, here you get an energy spectrum that scales as k to the -5/3. And this prediction of the energy spectrum is very well, it has been verified in plenty of cases in fluids. Okay, this is one of those, one of the experiments that have confirmed the Kolmogorov spectrum. So different numbers, like? Yeah. This is incompressible isotropic turbulence. So it's very specific. It's a very specific system. There is evidence of Kolmogorov-like turbulent cascade in space. Okay, so this is a typical example of the magnetic field energy spectrum in the solar wind at 1 astronomical unit. But you will notice that it's kind of much more complex with respect to the previous plot from standard fluids. We have what's defined here, the injection range. It has a power law to F to the -1. So, okay, So here it's frequency rather than space k. Okay, you will see this perhaps later in the laboratory. How do you go from F to K or not? Yes. Okay. Good. F to the minus 1. Then here it is our inertial range. A lot of effort is going to determining the spectral slope of this. Okay. And then there is a breaking point here, and it is followed from a subinertial range. This happens when you are hitting the intrinsic scales of plasmas. Could be the ion Larmor radius or ion inertial length, whatever comes first. And so rather than a standard dissipation range, you have this subinertial range where you have, other physics comes in. Okay, kinetic effects. So what I'm going to focus on is in this inertial range, which is at scales larger than proton kinetic scales, and therefore it falls into the MHD regime. Before going to that, I'm going to show you a couple of other examples. How much time do I have? 20 minutes. Oh, okay, plenty. Okay, so similar cascades are observed in the magnetosheath here. This is the magnetotail. And also in interplanetary space, there is evidence of Kolmogorov cascade. So here these are old data. This is really this spectrum refers to density fluctuations, okay? So these have been measured indirectly through radio scintillation. And this on the right, in fact, they found the same result. These are direct measurements of density fluctuations in interstellar, from Voyagers, okay, when it went supposedly in beyond our solar system. So, all right. So we have seen that there is plenty of evidence, okay, of a turbulent cascade similar to what Kolmogorov has described for fluids in magnetized plasmas. Okay. However, there are fundamental differences. There are similarities, but also important differences. First of all, MHD contains two scales. Okay, there is the scale associated to wave propagation. Specifically, we will see the Alven time. Okay. And the fluid time scale, like in Navier-Stokes, okay? Magnetized plasmas have also a magnetic field, so isotropy is broken. The presence of a mean magnetic field introduces a preferential direction. And because there is a magnetic field, now we have two fields, the velocity and the magnetic field, okay, that are coupled together. So these add complexity. And just like for fluids, also in MHD, really what has been studied a lot is incompressible MHD. And the building blocks of incompressible MHD turbulence are Alven waves, okay? And I'm going to skip through this because now you are experts, right? Yes. So here are, for your reference, your incompressible MHD equations, okay? Like Marco said yesterday, we can introduce, instead of using UMB, it's convenient to use Z plus and Z minus, the Sasser fields, okay? So you can combine the momentum equation with the induction equation. You can appropriately sum and subtract them. So that from two equations, one for U and one for B, you get other two equations, one for Z plus and the other for Z minus. And so these equations are nice because we can kind of recover some symmetries of Navier-Stokes equations with some differences. First difference is this term here, okay? This is a linear propagation term. So if you forget about what's on the right-hand side, okay, you obtain a simple advection equation for Z plus and Z minus. So now you can see that they really represent Alvenic signals that propagate parallel or anti-parallel to the mean magnetic field. So VA is the Alven speed associated to the mean magnetic field. Okay. So this is the first difference. The second important difference is that what was the U dot grad U, the nonlinear term? Well, now you can see that it mixes the two fields, the Z plus and Z minus. So what that means is that the nonlinearity in incompressible MHD is triggered by the interaction of counter-propagating Alvenic modes. And so we have two time scales. Right? So we have what I called earlier the nonlinear advection time, okay? Z minus plus dot grad, okay? And then there is the linear propagation time. And so depending on what is shorter, okay, or what terms here is bigger, well, then it determines a specific regime of turbulence, okay? So turbulence is said to be weak, okay, when the linear propagation term dominates over the nonlinear advection time. So what that means is that the Alven time associated, so lambda over VA is shorter, okay, than the nonlinear advection time. The opposite limit defines the strong turbulence regime. There are countless phenomenologies of MHD turbulence, which I'm not going to review, but I'm going to discuss two that serve, in fact, as the basis for many variations on the theme. So the first phenomenology, in fact, the first phenomenology of MHD turbulence was introduced by Roshnikov and Kraichnan, and it falls into the category of isotropic weak turbulence. So they assume, the hypothesis is that turbulence is driven by the interaction of Alvenic vortices, okay? And the interactions are weak, okay? So the shorter time scale is dictated by the Alven propagation time. And during a given interaction, these vortices are not deformed much, okay? So the second hypothesis is isotropy. One second. So isotropy, which means that they do not distinguish between scales parallel and perpendicular with respect to the mean field. Yes?
Curious, I've always sort of been confused by this with MHD turbulence.
Yeah.
How do we get from field line propagating alpine waves to eddies?
I mean, okay. Well, they're not.
And then you can see like simulations of MHD turbulence.
Yes.
You're looking in plane perpendicular to the background field. You see these circles that are representing
right.
current waves. But
That's okay. No, so okay, forget about waves. Like we're talking about like structures, okay, which are Alvenic. Well, we are talking about structures represented by fluctuations in velocity and magnetic field, okay, which if they were non-interacting, non-linear, so if the amplitudes were very small, this would represent signals that propagated the Alven speed. Does it pass? No? Yes?
So is it better to think about this not as, when we talk about wave propagation, like the first thing that comes to my mind is this nice smooth sinusoidal,
Yeah.
But somebody plucked a string.
Somebody what?
Plucked a string is really what's happening. Like somebody hit the system and we get waves coming.
Yeah.
We get waves and all the different modes coming out, but it's not the nice sinusoidal wave.
No, so, okay.
Okay,
No, yeah, no, when we are talking about like nonlinear systems, really, there is a big discussions on whether we can use even the name wave or not. Marco, you want to say something? It's a little. Yeah, but right. So when we are talking about like turbulent settings, especially when we talk about strong turbulence, you really have to forget about the concept of a nice sinusoidal wave. It's large amplitude structures which are deformed and, you know, yeah. All right, so so the weakness of the hypothesis is here in this inequality, and the isotropy is in the second, is not an equality, okay? This they approximate lambda parallel of the order of lambda per, okay? So that makes the cascade isotropic. Now, because the dominant, the shortest time scale is the Alven time, okay? These Alvenic eddies, let me bear with me with this analogy just for the sake of communication, will interact during a time delta t, which is determined by the Alven time. That's the hypothesis, okay? But because, all right, so during this single interaction, during one of these interactions, there's gonna be a variation of the velocity, delta u, equal to delta t u squared over lambda. This comes from the momentum equation, okay? You have delta u over delta t, okay? Equal of the order of u dot grad u, okay? That's this term here. And then we plug in our estimated length of delta t, okay? The weakness enters here in the fact that delta u over u is much smaller than 1. And so to have a sufficiently strong perturbation delta u, you need many of these single collisions. And it is assumed that the process, okay, where is it? Oops, I'm going back. All right. So you need n of these collisions of Alvenic vortices, which are assumed to be random. Because they're random, then the standard deviation of a random process scales as the square root of n. This is again the central limit theorem of this morning. All right, and so, well, how much is this n? Does this n need to be? Okay, well, we impose the delta u over u will be 1. Okay, so that's big enough to ensure that the Alvenic eddy has deformed nonlinearly. And so you impose that the ratio delta u over u is 1, and that gives you a number of collisions that is approximately equal to VA, the Alven speed, divided by u lambda to the square, okay? So the nonlinear times, therefore, will correspond to the n of these collisions times the time of delta t of the single collision, okay? So you end up having a much longer nonlinear time than Kolmogorov, okay? And so this ends up affecting the turbulent cascade. So you have all of the elements, in fact, to derive this energy spectrum on your own. Once you have determined the nonlinear time, okay, you apply the constraint of, scale-free energy transfer rate, and you get your spectrum. So you can do that. The major limitation of this model is that turbulence is assumed to be isotropic, which is not what we observe, neither in observations nor in simulations, okay? If there is a mean magnetic field, it's easier to break a filament across the magnetic field rather than along the magnetic field, okay? So the second phenomenology introduced, that's one of the most famous, is by Goldrake and Sridhar, who in fact introduced anisotropy, okay? And their phenomenology is based on two assumptions. Critical balance, okay? So the two time scales are of the same order of magnitude, and strong turbulence, so that the nonlinear time is postulated to be the analogous of the Kolmogorov eddy turnover time, okay? With the exception that instead of lambda, you have lambda perp. So again, you have at this point all of the ingredients to obtain the corresponding predicted energy spectra. Okay? Now, how well does this phenomenology do to reproduce observations? So this is another example of the magnetic energy spectrum at different radial distances from the sun. So these are taken by Parker Solar Probe, okay? So what we find is that this spectral slope ranges from -3/2 to -5/3. So in between the Roshnikov and Krashevan weak thing and the Goldrake and Sridhar strong turbulence, okay? And more or less, that's always been more or less the debate on whether it's -3/2 or 5/3. But it appears, in fact, that the turbulence is evolving with radial distance. The other aspect that is found, in fact, is that anisotropy, that the turbulent cascade is anisotropic, and at least at one astronomical unit, it seems to tend toward the critically balanced state. In particular, this lower plot here shows the spectral index as a function of the angle between B and K, okay? So when you are nearly parallel, you have a -2 as predicted by the critical balance. And then when you are perp, you are close to -5/3. There, other scalings have also been reported, which points to the fact that there is not really a conclusive answer as to what theory explains turbulence in the solar wind. If I have a few minutes, I'm not sure, and I want to kill you also, but there are many other issues that are not explained by this theory. The fact that velocity and magnetic field display different spectra. And how much time do you have?
5 minutes.
Okay. Sure. That's enough. So the other thing I wanted to point out, which is quite interesting, I want to close the circle at this point. There are two types of wind with two types of turbulence, okay? So this plot here, this plot here shows the velocity, okay, of the solar wind. So you have fast wind and slow wind, okay? And above and below, there is the calculated spectrum of Z plus and Z minus. So in the slow wind, what you find is that the Z plus and Z minuses are balanced. I mean, they have the same content of energy. These two lines are nearly superposed. Good. The fast wind, if we look at that, it's completely different. Yes. Yes. Yes, because as we said, repetitively, we have an Alvenic wind. So we have a non-Alvenic wind, which is this. This is standard. This reproduces the observations of this kind of turbulence is consistent with the theories, the phenomenologies, and it is consistent with the hypotheses underlying those phenomenologies. Alvenic turbulence is highly imbalanced. So it shows properties that are consistent, again, with the phenomenologies, but it is not consistent with the hypotheses, okay? So that's the big, I guess, one of the big open conundrums, if you like, of Alvenic turbulence. I think that's the main bottom line. I have a few extra slides to reinforce this argument, okay? So this is another way to look at the same thing. So this is the distribution of solar wind data points in the parameter space defined by cross-helicity and velocity of the wind. The cross-helicity is defined here is a scalar quantity. So we love scalar quantities that measure the imbalance, okay, of Z plus and Z minus. And so the slow wind is, so in fact, what's coming to light is that there are two types of slow wind. One that's the standard balanced, zero cross-helicity, nearly zero. And then there is a slow wind that is also highly galvanic, so cross-helicity nearly 1. And this is the standard galvanic wind. This blob here, fast and highly galvanic. Sorry, what?
For the magnetic helicity, sigma m, do we get a similar division?
Sigma m. I don't know. Well, there is sigma r, the residual energy, so the imbalance of kinetic and magnetic energy, okay? So in principle, if you're very galvanic, you will not have, so sigma r should be 0, okay? Because magnetic energy and kinetic energy are exactly balanced by definition, right? And instead it's magnetically dominated when you have nearly zero cross-helicity. Is that what you're referring, maybe? And so the devil is in the details, because even when we are highly imbalanced, we observe an excess of magnetic energy, right? Which should not be there. And we're trying to understand what causes it. But honestly, I don't know about the sigma m. Magnetic helicity. Magnetic helicity is also not well defined because it's gauge. It's also gauge dependent. What? But it is gauge dependent. No, is not that also part of the problem? No. Yeah, that's right. So, yes, if you had multiple, yeah. Yeah. So, right on.
Is this a good stop?
Yes, I think so. So I was just gonna say, reinforce the idea that there is turbulence, but yet coherence, which is kind of very interesting aspect of this galvanic turbulence. I'll just conclude that while it's not surprising that the phenomenologies do not exactly work well because they assume homogeneity, for example. The solar wind is certainly not homogeneous because it's in expanding medium. And so these are really the starting point equations to study how these fluctuations evolve in the solar wind. And reflection, which is this, the inhomogeneity of the flow. So because it is expanding, it's important because it reflects waves, okay? And so one way, so we know now that we need counter-propagating waves to trigger the turbulent cascade, right? And so reflection can help, okay? Because it reflects the wave. And so there is also another model, which is the reflection-driven turbulence. That's also an important paradigm to study, to study turbulence in the solar wind. And I close here. Thank you very much.
Got questions? All right.
Okay, so I understand there's different types of turbulence, and I imagine a significant reason is because of differences in key sort of scaling parameters of the plasma. But are there sort of fingerprints of the mechanisms which cause the turbulence, say waves in the corona versus Kelvin-Helmholtz instabilities in Earth meteor sheath? Would those lead to significant differences in the kinds of turbulence you observe?
What's the origin of turbulence? So there are many ways you can have perturbations. You can have injection, like in the case of the sun, or you can have an instability, like a Kelvin-Helmholtz, that would lead to I'm sorry, to turbulence. All right. Now, I don't think I have a good answer to your question. So the question is if the way turbulence is initiated leaves an imprint,
Yes.
okay, in the spectrum. Wow. Well, okay, possibly. In the case of the solar wind, for example, I mentioned the energy containing range. Okay, well, that's where so the energy containing range is where, supposedly the source is, okay, of whatever triggers your turbulent cascade. So in the case of the solar wind, there is this f to the -1, okay? So some people believe that that's an imprint of what's happening on the sun, for example. It's a difficult question to answer, but that's an example where you can find, there are theories that seek imprints in the turbulent cascade. So that is possible, yeah. Well, yeah, I guess what is the bouncing?
No, the question is whether the different type of scale turbulence that you mentioned has something to do with the scaling actually. Like we see Kolmogorov scaling, which goes like -5/3, and other which goes by -7/3, etc. So whether the different type of turbulence has to do with have some connection with the scaling actually. The spectra.
So a different type of turbulence that gives rise to a different spectrum. Is that your question?
Yeah, I mean, slope, right?
Yeah.
Slope is if it is -5/3, it's Kolmogorov scaling. Is the different turbulence, the type of turbulence has connection with that?
Your question is if we have a different type of turbulence, what kind of scaling do we expect? Well, okay. Yeah, that's another good question, and it really depends on the system you're studying. So I don't have on top of my head numbers. I'm not a great how to say, I'm not passionate about the scaling laws per se. But I showed you an example of turbulence in the magnetosheath, okay? And I chose it ad hoc, that was showing a k to the f to the -5/3, okay? But if you analyze data in the magnetosheath, you can have a spectrum. So signatures, let's say that a spectrum is really a symptom that you have nonlinearities ongoing, okay? But if you have dominance of compressible modes, magnetosonic structures rather than incompressible organic fluctuation, the spectrum is the spectral slope is different. I don't remember the number. Okay, yeah.
So I know you've done a little bit of work on this, so I just wanted to ask you, since we have you in person, what do you think is the relationship between turbulence and switchbacks?
Oh, that was one of the right. I didn't finish my talk, and my last slides were challenges brought by the recent observations by Parker Solar Probe. And so as it ends up, this nicely both Albanic, coherent, and apparently turbulent state is permeated by switchbacks. So switchbacks are embedded in that turbulence. They're part of it. They're not, how do you say, they cannot prescind from the turbulence. They're in there. What's their role? That's one of the questions that people are trying to figure out. Somebody claims that nonlinearities are enhanced during intervals where you have switchbacks. Other instead perform other types of analysis and say that no, there is nothing special happening in switchbacks. Fact is they're highly coherent. The nonlinear term, therefore, in principle, is quenched. I don't have an answer. I mean, we're working on it, I guess. It's open field of research, interesting. What happens, it's possible that what I studied, for example, is that structures like those become unstable inevitably. All of these Albanic structures, if you do simulations or some stability analysis, you find that there's no way they're not supposed to be there. They're supposed to be unstable. And yet we find that they are nice, there, standing there, propagating. So we are trying to put all of these pieces together. Yep. Yeah, there's one question.
So for the Kolmogorov scaling, we had the assumption of incompressible and isotropic, yes. So my question is, does it go both ways? So when we find the Kolmogorov scaling in observations, can we directly say that the plasma behaves more, at least in a dominant way, as an incompressible fluid and isotropic?
I wouldn't do it, but what you can do is that, okay, you find this, let's say, this symptom of, okay, it looks like a Kolmogorov nonlinear turbulent cascade, and then you have to go and take a look at how the signal look like. As it turns out, in the solar wind, they're nearly incompressible, actually, right? So this part is consistent. However, there are other things that are inconsistent, let's say, with the hypothesis that underlie Kolmogorov in the solar wind, at least. The fact that it is not really isotropic, it's an inhomogeneous medium, okay? So how does that come into play? And I had in mind something else I wanted to say that now is left through my mind. Right, and also the fact that we do observe that it is incompressible, so density fluctuations are very, very, like 10%. The question is, how is it possible? Because that's not supposed to be the case. So one of the questions to understand also is, how do you end up having this incompressible nonlinear state with incompressible Albanian waves, and yet this appears to be, with ongoing nonlinearities? So there are these kind of apparent contradictions that make, I think, the topic of Albanic turbulence in the solar wind quite fascinating. I don't know if I answered your question. So, I mean, do not assume, always verify.
Yes. Thank you.